All right, in that last example, we looked at the average rates of change of a function over intervals about a particular point in order to estimate the average rate of change or the rate of change at that point. So that brings us to the concept of instantaneous rate of change. So if we're trying to find the instantaneous rate of change of a function at a particular point, we define that to be the limit of the average rates of change over shorter and shorter intervals around that point. All right, so let's take a look at let's try to visualize what we're what we're talking about. All right, so we can, if we find the average rate of change between 2 points, the average rate of change is essentially the slope of the line between those 2 points. And we can take, if we're trying to find, say, the average or the instantaneous rate of change at this point A, then we can take the average rate of change. We can find the average rate of change over intervals that are closer and closer together, so that this B value is getting closer and closer to A. And we can get as close as we like, and we can look at what that slope is approaching, and in order to determine the instantaneous rate of change at the point A. All right. So another way to think of it is that you can think of zooming in on that curve, and as you zoom in closer and closer and closer, the line looks more linear, and then the slope of that line is the instantaneous rate of change. And that's also the derivative. So the derivative of a function at a particular value, x equals a, is defined to be the instantaneous rate of change at x equals a. And you can visualize it as the slope of the graph at a, or you can think of it as the slope of the tangent line to the curve at a. And a tangent line is just a line that touches at one point. Okay. All right. So if the function is increasing, right, then the derivative is greater than 0, right? So it's increasing, so the change in y is getting bigger as you change, as you go in the positive direction for x, right? And so the slope is positive, which means the derivative is positive, right? Because the derivative is essentially the slope of the tangent line at that point. And if f is decreasing, then the derivative will be negative at that point, okay? Which means that it's decreasing because the value of the function decreases as you increase the independent variable x. And so that means the slope is negative, which means that the derivative is negative. All right, let's take a look at this next example here. And all right, so here we're actually given a function as a formula, and we're asked to find the average rate of change over these intervals. All right, but the intervals are, we're looking at t values. Well, actually, this should be x, right? This should be x because my variable up here is x. All right, so we're looking at intervals about around 2. So we're looking at, we're trying to find the average rate of change from 2 to 2 plus h, where h is given here. So this first interval, we're looking at the average rate of change from 2 to 2.1, 2 to 2.01, 2 to 2.001. All right. So I need to calculate the average rates of change, and I can just plug those values into the formula to find it. Now, so I know that g of 2 is equal to, we're going to get 4 minus 4 plus 5, right? So that's just equal to 5. Now what I want to do is I want to find g of 2 plus h and subtract g at 2, and then divide that by 2 plus h, right? And then minus 2. So essentially that cancels, and it's just over h. So it would be good to have that we have g of 2 here, so I can plug that in. So I'm going to find g at 2.1, g at 2.01, and g at 2.001, and then it'll be easier to calculate these values. Okay, so when I plug in 2.1 to this original formula, x squared minus 2x plus 5, I get 5.21. Plug in 2.01, I get 5.0201, and when I plug in 2.001, I get 5.0020001. Okay, so now I just need to take the difference between these g values at 2.1, or 2.01 and 2.001, and subtract 5 from it, and then divide by the h value, 0.1 or 0.01 or 0.001. Okay, so I'm just going to take, again, I'm just going to plug it into this formula, and I got different values of the h though. All right, so when I do that, I get, for the average rate of change when h is 0.1, I got 2.1. When h is 0.01, I get 2.01. And when h is 0.001, I got 2.001. All right, so now I have the average rates of change over those smaller and smaller intervals. So essentially what I'm doing is I have this curve, right? Looks something like that, and I'm just, let's say this is 2, right? This is 2, and then I'm finding slopes that are getting as the the difference between the x values, which is h, is getting smaller and smaller. All right, so based on that, based on my results, it looks like my average rate of change is approaching 2, right? So I would say, if I was going to estimate g prime of 2, right? Remember that the derivative is the instantaneous rate of change at that point, which is the limit as those intervals get smaller and smaller. All right, so I'm going to say that my derivative at 2 appears to be approaching 2. Okay. All right. So now let's look at this more generally. What I want to do is I want to, instead of just choosing a particular value of x, here we chose 2, so we're trying to find the average rate of change at 2. But we can also just do it more generally. We can just choose a value of, arbitrary value x, and then we can add a little bit to it and find the derivative of a function at any point. All right, so essentially we're getting the derivative function. But first of all, what I need is g of x plus h. So what does that mean? That just means that wherever I have x in the formula, I'm going to replace it with x plus h, right? So the input now is x plus h. So I don't know if I can get the formula on at the same time. I guess I can. Okay, so we have x squared. So rather than x, I'm going to write x plus h squared. I'm just replacing x with x plus h. And then minus 2 times x plus h, and then plus 5. All right, so I'm calculating g of x plus h. All right, so I'm going to scroll back up to give me a little more room. All right, so I'm just gonna expand this out. So when I expand the x plus h, right, I square that out. So remember that square does not distribute, right? We had to FOIL it out. It's essentially x plus h times x plus h, right? And we can FOIL that out. So we get x squared plus 2hx plus h squared. And then I can distribute the negative 2, which is negative 2x minus 2h, and then plus 5. All right, so all I've done is just expand that out. And I don't know if that's simpler, but I'm going to need to do that down here. So down here now, I'm going to take that g of x plus h and subtract g of x and then subtract the delta x, which is x plus h minus x, which that just cancels, right? If I have x minus x, that's 0. So essentially I'm just dividing this by h. All right, so let's plug this in. We're finding delta y over delta x. All right, so I'm going to use the g of x plus h that I just found above, which is x squared plus 2hx plus h squared minus 2x minus 2h plus 5. Okay, it looks like a lot, but there's going to be some stuff that cancels here. Then I'm going to subtract the original g of x formula. So x squared, let's see, yeah, it's minus 2x plus 5. Okay. Now I'm subtracting this whole thing, so I need to distribute that negative, but I'm essentially subtracting everything. So this x squared will cancel, right? Because we got x squared, and then this is going to be minus x squared. I've also got a negative 2x, and when I subtract the negative over here, I have a plus 2x. So that goes away as well. And then I have a 5, and then when I distribute this negative, I've got a minus 5, so that's going to cancel as well. Now all of that is over h. Okay, so all right, let's clean that up and see what we have left. All right, so I've got 2hx plus h squared minus 2h. That's all that's left up there on the top, and that's all divided by h. Now notice I have a factor of h in each of these terms in the numerator, so I could factor that out. I'll have 2x plus h minus 2 left if I factor that out, and then you can see that those will cancel. Or you may just, recognize right away that you can just cancel the h in each term. You're essentially distributing a 1 over h. This dividing by h is the same as multiplying by 1 over h, and then you can think of using the distributor property. So either way, those h's cancel, and all we're left with is 2x plus h minus 2. All right, so that's nice. It simplifies down nicely there. What does the formula above represent? Okay, so now remember, this is an average rate of change. Average rate of change. Right? This is the formula for average rate of change, and it's the average rate of change over the interval from x to x plus h. So I'm just going to say that it represents the average rate of change. Over the interval from x to x plus h. All right. So now let's take a look at what happens as h approaches 0. Right? As h gets closer and closer to 0, which is essentially that h is the difference. It's the difference between x plus h and x, right? It's the delta x value. So I'm letting that delta x become smaller and smaller and smaller, and we can actually go to 0 when the formula is in this form, right? If h is 0, then we get the instantaneous rate of change, right? This becomes dy over dx, right? These are differentials. This is the instantaneous rate of change, which is also could be written as f prime of x. And so h is going to 0, so we just have 2x minus 2. Wow, nice simple formula, right? So now we have a formula for the derivative of the function. And we're asked to sketch a graph. Well, it's just going to be a line, right? So let's just sort of graph that line here. I'll just draw a little graph. It has a y-intercept of -2 and a slope of 2. So rise over run is 2, so it would intersect here at 1. And so we could draw a line between these 2 points. So actually, let's do this. Let me just use the line tool. That'd probably be easier. All right, I'm just going to draw a line that goes through those points. Okay. So there's a line. All right, so this is, I should label these axes. This is x, and this is not y, because I defined y to be f of x. This is actually f prime of x. I'll just label the x as f prime of x. So this is a graph of the derivative of the function. All right, so now if we want to know the instantaneous rate of change at any point on that function, the original function. Now this was actually, I was realizing this is g, not f. So I should make this g, right? And I should make this also a g, g prime of x. All right, so our original function was, g of x equals x squared minus 2x. I'll go back up here. Minus 2x plus 5, right? And so now we have the derivative of the function as a function, so we can find the instantaneous rate of change anywhere on that function. All right, I will meet you in the next video.